Good morning, good afternoon, good evening, depending on whichever part of the world you're joining us from. It is a complete pleasure to have you all today for our Instant Insight series of webinar. Today we'll be talking about the applications of Tribo-Rheometry in materials characterization. And so the outline of this talk, we're basically going to introduce just the concept of tribology and Tribo-Rheometry in general can be used for tribological measurements. Why are they one of the analytical instruments of choice for making these measurements? And then, so that'll be the first half of the talk. And then the second half of the talk, we'll talk a little bit about the different applications. We'll start with the basic lubricants and lubrication, which is the first thing that comes to our mind when we talk about tribology. But then we'll move into some of these unique applications that have developed over the years. So first, tribology, if you look at the etymology of this word, it is derived from two Greek prefixes, if you may. Tribos meaning rub or to rub, and ology, as we all know, is the study of. So literally translated, it means the study of rubbing or study of things that rub against each other. And more colloquially, we know this as friction. So anytime we know when we're talking about friction, there are multiple. And what happens at the end of that interaction or during that interaction? So do they adhere well, or do they generate a lot of heat? Does it cause wear and tear? These are the kind of things that, these are the kind of questions that tribology tries to answer. And so when we talk about, look at this in more detail, or at least around us, there's friction everywhere, from the soles of our shoes to the internal combustion engine to, and this was something baby oil, coatings that we apply. I never really realized that whenever I touch these materials, there's a sense of perception that I have developed, like just by, I think if I were to be blindfolded and touch certain products, I would be more adept. Each one of us could probably guess what general category this forms into. And this perception has become a very big industry driver to develop new products. And we are always talking about the performance or the reliability. So if you're looking at an osteoarthritic fluid substitute, then yeah, it has to have if it's going to go into the body, it has to perform the same kind of function that the synovial fluids typically perform. So there's this functionality element to it as well, which tribology tries to quantify. And traditionally, when we look, if we take a trip down memory during our high school days, and so we have two bodies, one moving relative to the other. So either both of them can be moving, or in a more simpler scenario, one is stationary and the other is moving. And so whichever direction like in this case, it's the top block that is moving, whichever direction it is moving, the friction force acts in the opposite direction. There's of course a normal force that is acting perpendicular, the shear stress to normal stress. That is the ratio of the two is what is termed as the coefficient of friction. Now, friction force itself is easy to understand. Yes, if it is going, it's definitely acting to impede the motion, and in some cases, it also acts to assist the motion of the material. So if we didn't have friction, we wouldn't be able to walk. Everybody would be moonwalking all over the place. So the load interact with each other. So if you have a small load force, what we are showing over here is that between the two mating surfaces, wherever the lubricant is present or not present, you have what these surface roughnesses. So material that appears perfectly smooth to the human eye will have some roughness in it. And these roughnesses can be represented in terms of peaks and valleys, or what we term as asperities. So as you press down on the material, this plays a very important role in calculation of coefficient of friction. So with this discussion, now we can appreciate that when we are trying to make a tribological measurement, it requires three terms. One is the shear stress, second is the normal stress, and the third is if the objects are moving with respect to one another, you need a very nice way, or a very accurate way I should say, of measuring the speed of the motion or along which is causing this entire friction. as a function of the sliding speed. And this curve is called the Tribeck curve. We're going to explain some of the features in this curve in more detail as we go along the presentation. But as you can understand from here, the coefficient of friction is not a constant value. It is heavily dependent, amongst other things, on the sliding speed. So whether the objects are moving slowly versus if they're moving fast against one another will have a big impact on the measured coefficient of friction. Tribology and making those measurements using a rheometer. And so we're going to perform the same kind of friction measurements that we discussed up until now using the rheometer as an analytical tool. And one thing we can all appreciate, especially so a lot of the materials that we work with today, okay, let's just for a moment think about all the different materials that we work with today. They can broadly be classified either as simple flow and intricate set of characteristics in terms of flow, and a rheometer is a very powerful tool in making those measurements and trying to get a complete picture of how the material will flow when it is subjected to a deformation, right? So if you look at, for example, peanut oil versus if you look at cocoa butter, they'll have completely different sets of flow properties. We'll have more examples where we'll show how these flow properties will differ, used at different shear rates during its application. We also make the rheometer for more powerful measurements to get information right at the molecular level. And what we typically measure is called viscoelasticity. I won't go into a whole lot of detail right now about viscoelasticity in general as a concept, but what we can appreciate is that depending on whether you're working with something like mineral oil, skin cream, PDMS or hydrogel, you can see that the viscoelastic is powerful and in fact the only tool that can make these measurements. So why do we use this rheometer to make friction measurements? Because first of all, because of the nature of the measurements we talked about in the previous slides, in general, a rheometer is very sensitive to low forces. So if you're trying to measure what the frictional properties are at low forces, or what we call as torque, the rheometer is very well adept to make those measurements. So while it can make rotation, or while it can perform measurements along the shear direction, it can also make measurements in the normal direction. And it can also at the same time control the amount of force that you're applying in the normal direction. So you can press the materials by different extents and you can make these changes in very small amounts much more adeptly than any other instrument that is out there. And then at the same time, because rotational, in what we'll talk about is in rotational velocity. So you can control a wide range of sliding speeds, and essentially you can therefore get the entire, I wouldn't say you can get the entire Tribeck curve every time, but you can get a significant chunk of that Tribeck curve using a rheometer. The other benefit, of course, is that a rheometer will provide excellent temperature control because it is all the mechanical measurements and all the flow measurement instrument that is out there. And plus, what we'll talk about in the subsequent slides is that you will see how easy it is to modify the surfaces. So if you have 3 different surfaces that you want to make if you want to study the tribology of these 3 surfaces under different conditions, these modifications can be made very easily on a Tribo-Rheometer. And of course, the benefit is a lot either to get the flow profile or to get the viscoelastic measurements. Adding tribology to that measurement is a very simple and a modular option that we offer today, where you can make these measurements with relative ease. And so, just conceptually, if you look at the traditional diagram for what we talked about, how coefficient of friction is measured, except it's in a circular or a rotational frame of reference. So in this example, I've kind of exaggerated the gap, but if you look at it very closely, or if I had to blow up into it, these surfaces are essentially in contact. One surface is fixed, the other surface is rotating. You are making measurements or controlling the angular velocity, the torque, the angular displacement, which is related to the angular velocity, which is how it's controlled, and you basically a function of the torque, which is indicated by the letter M. The normal stress is also something that is measured directly using the instrument, and that is a function of the normal force that is generated during these measurements, or the normal force that you as a user have applied between the two surfaces in contact. So you get the mu by taking the ratio of the two, and the sliding speed you are using. So by making these, we basically can perform measurements of all these three parameters, what I like to call as the trifecta of tribological measurements, right? If we don't count temperature into it. Temperature, of course, forms that fourth quadrant. Now, for those of you who are joining us today for the first time, first of all, welcome to TA Instruments. We hope to see you again and again in these webinars and another professional, the Aries G2, which is the only rheometer out there today where the motor, which applies the deformation, and transducer, which measures the forces and the torques generated from that deformation, these are separated. So this is the only design that is out there, and it is unparalleled in terms of its performance or in terms of making certain sets of measurements. All right. Why do I say that? Especially in the output of all, it has the torque rebalance transducer. So the rebalance, when you look at the word rebalance transducer, essentially what it means is that this transducer is not moving when it's making the measurement. We are going to do everything possible to maintain it in a null position. So whatever amount of torque I have to put in a conceptual manner of speaking, to maintain this null position is equal to the torque that is generated when the material is deformed, a wide range. And because these are making measurements of stresses generated in the shear direction, you are very well adept to make shear stress measurements. Oops. At the same time, in that transducer, there's a different transducer that is independently now making normal stress measurements. So when you look at these, the concept is the same. It is preventing the torque either generated, and by the same token, when you push down on the material, that's how it is measuring the normal force. And again, the benefit of this whole technology is it's accurate for sure, it is sensitive, and at the same time, it is extremely rapid in its response. So even the smallest changes in the normal force, you can detect very easily. Right? And then the motor, which is the bottom part of this instrument, completely decoupled from the top part. So brushless DC motor, which is again a unique technology. It has very high stiffness, and it is extremely concentric, and it has an optical encoder built into it, or is part of this entire setup. All of these features now allow you to control the sliding speed or the angular velocity in a very, very controlled fashion. So you can control the angular velocity from extremely slow to extremely fast as a function of the sliding speed. Now, the environmental systems that it offers, it's the forced convection oven, which is the oven, and the Peltier system, which is the Peltier. Both of these, of course, are available on the rheometer, and the Tribo-Rheometry accessory is compatible with both of these environmental systems. It depends on what temperature ranges you're looking to perform the measurements at. Clear this year. And it is a combined motor and transducer rheometer, which is slightly different than the Aries G2. But where it stands out is it is in this class of rheometers, it is by far the most sensitive rheometer. It is extremely easy to use and very modular and very versatile. So you might get the Tribo-Rheometry setup today, or you can with this particular rheometer, and tomorrow if you need a microscope, you can add to this. It offers accessories. The Discovery Hybrid series offers even more accessories. Okay, and so again, when you look at why is this possible, one of the first things that will stand out is that this is not your conventional rheometer with a traditional air bearing. It actually has a magnetic thrust bearing, which means the amount of air surrounding the bearings has been reduced by about 70% is reduced. Okay, so that allows you to make shear stress measurements for these for tribological purposes at the very low end of the shear stresses. At the same time, the overall construction of this entire rheometer is made out of, it's very rigid, and this is important because you want your measuring system to be stiffer than the sample. You don't want your measuring system to be moving around when your test box generated can get pretty high. So you definitely want something that is stiff, and the construction of this rheometer allows you to make these measurements. So now we've covered the low shear stress regime, and you've covered the high shear stress regime with the same instrument. And of course, it has the force rebalance transducer, which makes the normal force measurements, and so that allows you to make normal stress measurements very rapidly and very facilely. Reader, so it allows you to control displacement very accurately, measure displacement, I should say, very accurately. So the overall resolution in the displacement is extremely high, but at the end of it, you are still able to control the sliding speed, which, as you can see from the graph, it's a function of the angular velocity, which is further a function of the angular displacement. So you can control the sliding speed very facilely. The Discovery series, you can use it with the Tribo-Rheometry accessories. The other modular option that the Discovery series offers, and is unique in this case, is that it can control the relative humidity and temperature simultaneously, which is very useful when you think about it, because a lot of the materials that we develop in the lab, eventually when they go out in the field, they are not experiencing the same air-conditioned controlled humidity environment that we have subjected them to in the lab. It will allow you to perform tribological measurements under these extreme conditions. So this is something that is very powerful in the Discovery series of rheometers. And so to summarize again, both these rheometers are extremely excellent in terms of making these measurements, both from the fundamental rheological measurement standpoint as well as for tribo-rheometric standpoints. Offer about the same temperature sliding speed, so we don't expect the user to go in and calculate them. You're welcome to, but we'll do a lot of this work for you. So we'll give you the sliding speed, we'll give you the load force, we'll give you the friction force, we'll give you the coefficient of friction, we'll give you the stresses if we can calculate the stresses in a setup, and we'll also give you other dimensionless quantities that are typically used in these measurements. Traditional rheological geometry that you might have seen is that it is always, at least the ones that we offer from TA, will have a beam coupling. And this beam coupling is there by design, because when you're pushing down on the material, you want to have some sort of compliance, but without compromising any of the overall stiffness of the material. And so it allows you to push down on the material with much greater control. And remember that the coupling is, even when you introduce the compliance in the system, it is still making those measurements very adeptly. If you had compliance in the normal force measuring system, you have a problem where the system itself is contributing to some of those measurements. We don't want that. We want the measurements strictly from the material. And at the same time, because this beam coupling is at the top, when you push down on a material, the whole system misses off the shaft and through the FRT, and that's where the measurement is being made. And we have 4 different setups that we offer. One which is called as a ring on plate. So you have plate at the bottom, ring at the top. These names are very self-explanatory. Ball on 3 plates. You have a ball at the top, and you have 3 plates arranged at an angle at the bottom. You have 3 balls on a plate where you have the ball on the top, and there are 3 balls at the bottom. Each of these geometries, you can swap it out very easily. There's a very good webinar on our website where we introduce Tribo-Rheometry, which is kind of, I would say, a prelude to what we are going to talk about today. but it goes into a lot of detail into the hardware and also presents some very interesting applications apart from the ones that we are discussing today. So, all right, so that brings us to the end of the first part. One of the things that I will emphasize before we move to the next part is that when you're making friction measurements, there are three key criteria you need to be aware about. First is the surface itself. So whether you're making, what is the nature of the surfaces that is coming in contact with each other? Is it skin on skin, so you have skin substitutes? All of those variables will start affecting the measurement. So remember, the friction of a material is not an intrinsic material property like viscosity or modulus. It is heavily dependent on the system where how you're making the measurement, and you can translate it onto the field as well. It is heavily dependent on how the material will interact with the moving. Would have very good properties in an internal combustion engine, but if you were to use it, I don't know, let's say as a lubricant for ice skating, it won't work. Just the nature of the surfaces is completely different. Okay. The roughness of the surfaces, of course, is one of the key criteria that governs this entire process. The second key criteria, I would say, is the test parameter itself. So the sliding speed of the Strybeck curve, that it starts affecting the coefficient of friction. Temperature with any mechanical measurement, very important criteria. Load force, we talked about how they will start influencing the way asperities interact with each other. One good way to select what an appropriate load force is to think about the load forces the material will experience during the application. So for example, mouthfeel, typically 1 to 3 newtons. And the third criteria, of course, is the geometry. So you can have the exact same lubricant, exact same material, and you measure it on a ring on plate versus 3 balls on a plate, and the Strybeck curve will look different. Just because the area of contact is different, the geometry itself is different, and so the contact stresses start changing. Okay, here is just one example showing how the load force will start affecting that Strybeck curve. So what is that, for the same setup, as you start increasing the load force, you are now improving the overall lubrication because the fluid is able to support the load better. And so as you press down on the material more and more and go to higher speeds, it starts changing the coefficient of friction at higher speeds. See, at lower speeds, all the data is kind of overlapped. So this is again showing you a very good example. Here we are talking about PVC on a stainless steel part of the talk, where we'll talk about the different applications. And I'd be remiss if I didn't start off with the concept of lubrication, which was the main core application which allowed this field to mature to the level where it is right now. And so in any lubricated system, the Strybeck curve can be split up into 3 different parts. One where the coefficient of friction starts decreasing and kind of remains flat, which is at slow speeds. This area is called boundary increasing sliding speed. That's the mixed lubrication regime. And the third regime where the coefficient of friction starts to increase again, and this is the hydrodynamic lubrication regime. So what do these individual regimes mean? Right? So in boundary lubrication, your asperities are just basically in contact with each other right now. The lubricant is there, but because the relative motion between the materials is very low or very little, is the resistance to the force, is because of the asperities interlocking with each other. And so the system can move at slow speeds. One of the things I would like to highlight as we go through these different regimes is quite often in literature you will come across this term called as the lambda ratio. The lambda ratio is the thickness of the fluid film between the two surfaces compared to the overall roughness of the surface. Valley height, if it is 1 micrometer, in typical boundary lubrication system, the overall fluid film thickness is 1.2 micrometers. I'm giving you a conceptual number just to understand how lambda ratio starts playing a role in lubrication. Now, as the relative speed increases, the asperities also, the fluid starts moving between the asperities and slide over one another, which is what the lubricant was designed to do. And you can appreciate, because now the lubricant is starting to get more and more in this interface, the fluid film thickness starts increasing. The surface roughness for the most part remains the same, so your lambda ratio also starts increasing. And as you increase the speed further, now these fluids, there's no solid-solid contact. Now, I would say just lubricating it, there is another opposing force, that is the hydrodynamic force of the lubricant. So think about it this way: if you have something that is extremely viscous between the two surfaces and you move into the hydrodynamic lubrication regime, that viscosity of that material is going to offer some resistance to the motion of this material. It's what we can think about as a drag force of sorts. And so while the friction is still lower than what it would higher coefficient of friction. Okay? And this is again, when you look at core lubricant and its properties as a lubricant, these things come into picture. And so lubrication and rheology, based on our last slide, I hope I've been able to convince you, they're interrelated. So for example, now if you look at an engine oil lubricant, and I keep revisiting this just because I'm a car aficionado myself, a good educational example. If you look at an engine oil lubricant, it requires a high enough of a viscosity. So if you start increasing the temperature, as would happen in an internal combustion engine, and the oil becomes too thin, then it's just going to slip out between the gaps and the lubrication will not be very effective. But if it remains too high, then your if it remains too engine chamber. So you see, while lubrication of engine oil is very important and we need Strybeck curves and everything, to understand why it's behaving the way it's behaving, a corresponding rheological measurement is worth 1,000 words, if I would say. So here, for example, we're showing some data where we took the researchers took base oil and they added some additives, low properties of the material. The viscosity became higher, and while the base oil was Newtonian, the dispersion itself showed slight amount of shear thinning, and this could be desirable, this could be undesirable, depends on the situation. But without knowing the flow properties, just looking at the lubrication properties will not give the complete picture. Vice versa, if you just look at the flow properties and don't look at the lubrication properties, that's also going right. And so this is something, an example, we won't go into a whole lot of details. That some examples I've taken from the previous webinar. They're explained in a lot more detail. But here we're just showing you how coefficient of friction changes as a function of sliding speed. Here we are making the measurement at 180 degrees Celsius, so very high temperature. And you can identify the different regimes, but at a very high level, you can at least appreciate that lubricant B is the material of choice over here. Along the same token, what we'd mostly be talking about is dynamic friction, but there is an important concept in tribology, which is static coefficient of friction, which is basically, for those of you who are familiar with rheology, this is akin to yield stress in rheology terms, which means the two surfaces are at rest, and they are at rest, and you're applying a force and they're not moving because the frictional force is resisting it. And so the response to, or the coefficient of friction that you measure under these set of conditions is called the static coefficient of friction. And again, here you can see, initially at low sliding, like when the sliding speeds are 0, because you're just increasing the torque acting on the system, and as the torque keeps on increasing, eventually the material starts moving, and that's when you see a big shift in the sliding speed. This is where, when you look at warm mix asphalt technology, a lot of or hot mix technology, a big amount of effort is driven to improve the processability of asphalt while laying down on the road without having to heat it up too much, which means if you're going to put the asphalt down, I won't go into the whole lot of details about the exact mechanism. The paper that I've cited over here is a very good reference that goes into the details at the molecular level. What I do want to show is that it has been shown that friction just plays a lot more important role than one would envision in terms of understanding why warm mix asphalts behave the way they do and how you can use these measurements to the overall mixed lubrication regime starts increasing. So at 100 degrees Celsius, at 20,000 micrometers per second, the friction starts increasing. But at 120 degrees Celsius, the friction is more or less, it's not constant, it's decreasing, but it doesn't start increasing until orders of magnitude ahead. And so this gives you a very nice idea about how the different additives that are added in this particular asphalt mixture to improve its processability is hyperbranched polymers. With a background in macromolecular science, I always get very intrigued by different molecular architectures. So while a conventional polymer, if you can think of it as a linear chain that is entangled with each other, the hyperbranched polymer or a dendrimer has a circular structure, and that offers a whole lot of different benefits. So for example, you can go to higher molecular weights and still maintain a lower size, which in turn translates to lower viscosity, hydration properties, right? And so when you look at the flow properties of these different materials, certain materials, in this particular study, they were looking at comparing the lubrication behavior of different materials. And so they took a bunch of commercially available lubricants, and they just found that compared to the shear thinning behavior in the commercial lubricants, these materials more or less exhibit than the other. What I want to show is one is different than the other. And the interesting thing is when they started investigating the use of these materials in terms of its lubricity, they found that the hyperbranched polymers, which are represented in the blue circles and blue triangles, have very comparable coefficient of friction properties, of tribological properties, compared to the conventional synthetic. These molecules have a globular structure. These act as tiny ball bearings between the two surfaces that allows it to offer the lubricity that you can see in the graph over here. Now with that, let's look at the application of this field in different consumer perception situations. So let's look at personal care products, and skin feel is something that is intimately tied with the frictional properties. So, and efficiency, of course, is an extremely important part of characterizing and understanding these materials. But when you introduce tribology, you actually get a second dimension, if you may, in terms of how it would be perceived at the end of the when the consumer is going to use it. So again, because your consumer is going to feel it with the hand, what we are going to do is, in order to understand, and another is vitroskin. Both of them are commonly used for as skin substitutes. Okay, and we're going to test first baby oil, cold cream, and body lotion. All of them have different rheological profiles and different formulations altogether. And so in the sliding speed window, which is typical like 1 to 10 mm per second, which is the typical window when an average person will rub their hands, you find that with the transport tape, of course, the baby oil has a higher vitroskin. So at first, it's not that it's going to replace any sensory panels, but at least when you're in the initial development stage, it allows you to understand how each material is going to behave, because this is the same kind of perception behavior that you will get from a sensory panel, which comprises of trained humans. And those are more expensive tests, so it allows you to kind of. Another example is toothpaste, and toothpaste, as we brush our teeth, of course, we don't like something that is extremely rubby, or we don't like something that's extremely fluid. So there's a balance that you have to strike over there. And so you can see that when you look at a gel toothpaste versus a whitening toothpaste, at low coefficients at low speeds, they look similar, but at high speeds, the gel toothpaste flow properties. So if you look at the viscosity of these two materials, um, at low speeds, they're more or less comparable, but as you go to higher speeds, the gel toothpaste it doesn't shear thin as much. So it has a higher viscosity. And again, when you go into the hydrodynamic drag side of things, a higher viscosity is going to impede the motion more. It's data that has been collected and definitely very, very useful. Where you look at BB creams versus long wear foundations and makeup or lipstick, each of these materials has its own intended function, and you can see how the coefficient of friction of each of these materials is quite different compared to one another. What is also interesting to note that within themselves, the overall repeatability of the data is excellent. And that is where the power of the rheometer is, that when you're using a ring on plate kind of a setup, you want to make sure that you trim the excess sample, because that excess sample can cause some extra drag and you don't want that affecting your measurements. This is very similar to the conventional rheological measurements as well. And again, we talk about this in the first part of the webinar, or the link below, where the first webinar we presented on Tribo-Rheology. The second application I want to talk about today is wondering where does surface coatings and friction come into picture. And think about every time you've felt the wall of your house when you were like just standing against it, and you start realizing, like when you go to different houses and you were placing your hand or your body against the wall, you feel you have a slightly different perception. And this perception is important. So because at the end of the day, if I am a consumer, I want a certain level of finish. One is, of course, the optical property. So whether it's flat gloss or matte or satin or semi-gloss, so that's the amount of light. And so the question, when you look at like just the bulk flow properties, of course, they'll be slightly different. Like for example, when we've taken the two kinds of paints, one is matte, another is semi-gloss, and you can clearly pick out the subtle differences between the shear thinning behavior. The matte paint, in fact, shows a much more pronounced zero shear viscosity. Add the second level of testing, if you may, and see if I can, first of all, get an additional data point of differentiation. And second of all, how can I use this information to understand the perception that a customer would have at the end of this whole process. And so we tested it on 3 different surfaces. I'm going to present the data on the silicone rubber. The first point that I want to make is that between the flat paint, which is on the much lower side, compared to matte to semi-gloss. Now, if you knew the exact composition of these materials and what was making it flat versus semi-gloss, we can, of course, delve into it, couple it with the rheological measurements, and you can understand why what is happening. The other thing from practical standpoint, what I want to highlight is that between stainless steel and transport tape, if you look at the bar charts on the right hand side, metal at the bottom and the paint surface is at the bottom. So if that's your setup, and when you try to make measurements with that setup, it actually starts showing differences. And that's mainly because the rubber is providing a lot more grip to start elucidating these subtle differences between the materials. Since we're talking about rubbers, let's move right into elastomers, and where you can see now what we've on the top of that plate. And you can see the benefit of using this setup over the traditional ring on 3 plates, where you would have to put a rubber, where you'd have to cut out and put the elastomer on 3 different plates. This is much more faster, and as I'll show you, it gives you a more wider spectrum of tests and conditions that you can simulate. Okay. So now, if you just take dry surfaces, so you have steel balls on the top, rubber at the bottom, you can, and at slower speeds, it has the coefficient of friction is more or less comparable to B and C. Now, if you add a layer of water and then perform the measurements, now you're simulating wet grip of this material. And you can see how the wet grip of the material is quite different. Wet grip starts showing differences at the lower sliding speed, and then as you start increasing the sliding speed, it becomes more and more comparable. So that's again the benefit of chili. Much more difficult to do on a ball on 3 plates. And the last set application, or the last set of applications I want to talk about is mouthfeel in food and beverages. This again, when you look at how a material feels when you eat it or as you are eating it, that perception is extremely, extremely important, more so than any other field in terms of consumer acceptability, because I certainly will not put anything in my mouth. Those are things that start making a big difference in terms of the overall perception of the material. And so the surface properties of the material, which are really the properties that we measure at the micrometer to nanometer scale, those are the ones that really start affecting the overall mouthfeel or the frictional properties that we're going to talk about. Now, which have a constant viscosity, but you can appreciate the fact that, and you can try this, if you try to spread honey on butter, it's going to be a much more daunting task compared to, let's say, spreading mayonnaise on bread. So honey on bread versus mayonnaise on bread is the classical rheological paradigm that we talk about. And because mayonnaise is shear thinning, as you start spreading it, you apply more and more shear to it, and it thins out and the viscosity reduces. So we are very well aware of this. Coefficient of friction is more or less comparable. But then as you go to higher and higher sliding speeds, which is where the hydrodynamic regime starts setting in, you start seeing that honey honey gives the perception of a much more higher coefficient of friction compared to something like mayonnaise or mustard. So all the other materials that are non-Newtonian have some structure to it. Honey is purely Newtonian, but more than that, it is much more viscous at those measurement in itself. If you take honey out from that equation and just look at those 5 non-Newtonian fluids, they also exhibit quite a significant amount of differences between the coefficient of friction. And again, the differences at this point would be tied into their intimate structure, the amount of fat that is present, any additives that are present, the subtle differences in the rheological profile. So that can become a webinar in itself, that it will start picking up these differences very, very easily. And we covered food tribology in a lot of detail in the first webinar that we had. So by all means, again, one more motivation for you guys to check it out. We talk about the mouthfeel of chocolate. And for people who are on the East Coast, this is getting close to lunchtime. So I hope I'm stoking up your hunger, and that's why I kept food tribology as the last topic, because hopefully that will. And so chocolate and yogurt, of course, and the data on chocolate has been published as an application note as well. So in summary, again, with all these examples, I hope I've been able to show you that friction, of course, is a very important measurement or tribology, but it is not an inherent material property. It is highly dependent on the system. So what are the two surfaces that you are measuring the friction between, and the lubricant or whatever the material is in between the two rubbing surfaces. We talked briefly about an example where it's used to process asphalt. We talked about how it translates into some of the consumer parameters like tacticity and lubrication and everything. And of course, friction, amongst other things, will depend on temperature and the speed at which the two surfaces are rubbing against each other. With that, again, thank you so very much for joining us today on the live. And with that, I'll be happy to take any questions.
Thanks, Yash. There's been quite a few questions that have come in. We probably won't get to all of them, but we will make sure to individually respond to every single question that came through. So here, let's start out with a few of the different questions. A lot of questions were about what kind of materials can we use? Like, are we able to measure friction force, like very thin films, like in the presence or no presence of a thin film? Are these all measurements we can make?
The short answer is yes, you can test any material as long as you can attach it to the geometry. And that's why we offer these four different configurations that are available on this.
And let's see, there is another question of if the lubricant is, so if you're using lubricant and it's a really low viscosity, is there something that can kind of hold it in place?
So if I understand the question correctly, you're asking if the lubricant has really low viscosity, can it still be held in place? Am I correct?
Yes, like can I make a measurement with the low viscosity lubricant where it's not going everywhere?
So yeah, so typically with lubricants, you work with higher forces. That's one. Second, because lubricants have a range of viscosities and are more flowy in that sense, you can often, that's why the ASTM method recommends the 4-ball setup. And when you look at the 4-ball setup, it actually, the entire lubricant is contained in this cylinder of sorts, and you can spin the top shaft or covers so that even if the lubricant does start exiting out of the gap at high speeds, it doesn't really start contaminating the rheometer or fly onto the user, both of which are not the end of the world. You can fix it, but that's the 4-ball setup is going to help you a lot in that regard.
That actually helps segue into another question. Well, there's so many different geometry. How do I select the right geometry?
Webinar, the first part of that webinar, that's on our website. So definitely. The second, I'll just summarize it briefly. As I said, with lubricants, as we just discussed, because it's going to fly around, the 4 balls is a good setup. For skin feel and mouth feel, where you need substrates that are simulating the skin or the tongue. The ring and plate is a good setup because you can have those substrates coming in. As we showed, that's a really nice setup when you want to modify surfaces very easily.
Great, that's really helpful. What is and we've talked a lot about rotational frictional coefficient of friction. What's the physical significance of the coefficient of static friction? Can we make that measurement experimentally with this setup?
Yes, absolutely. So think about static friction as the minimum amount. So if you have a light box and a heavy box, and you try to move this heavy box, you will require a larger amount of force to start the motion of that box. If you're trying to push it along the ground, the heavy box is going to offer a lot more resistance than the lighter box. Same way, think of it in terms of surface area. If you have a smaller surface area in contact versus a larger surface area, the larger surface area is the static coefficient of friction, right? The way we measure it, this is very easily done on the discovery rheometers because these are torque controlled rheometers. You start increasing the torque slowly. So your rheometer can apply as low as, I don't know, zero torque, so there's no current going into the motor, and then it can sequentially increase the amount of torque acting on the system. And essentially, you will start noticing the first point where the torque is, or the friction is increasing, which is a measure of the torque, but the sliding speed is 0. And then suddenly you will see that the sliding speed increases. So that's your measure of static coefficient of friction.
Great, that's really helpful. In due time, we'll do one more question. Just remember, if we didn't get to your question today, we will be answering them individually afterwards. But how does the lambda ratio help us understand the different lubricant
values? So when you have, if you look at the two surfaces, if you look at the height of that peak or the height of the valley, that is the measure of the surface roughness. The lambda ratio is basically the ratio of the surface roughness to the layer of the fluid film that is between these surfaces. So when you're in the boundary regime, this fluid, you go to the mixed regime, there's more fluid that starts lubricating these surfaces, allowing it to move more freely. And then as the speed increases, there's more and more fluid that starts separating the surfaces. So your fluid thickness now increases. Consequently, your lambda ratio increases because your surface roughness is still the same. And now you go into the hydrodynamic regime. So the lambda ratio is something that is quite useful in understanding what regime you are in. It's something that you will come across.
We really enjoyed your talk. And thank you everybody for attending. As we mentioned, there's a survey if you can answer that. And then also, if we didn't get to your question, we will be responding to them individually afterwards. But thank you all for your attendance, and we hope to see you at our next Instant Insights.
Thank you.